So you've probably heard the term quaternion before. It's this thing that pops up all over the place in game development because it has this amazing property of being not only able to represent rotations in 3D space, but also being able to smoothly translate between them. This might not seem like a big deal, especially since the built-in lerp method for C-frames already handles the rotation translation, and to be honest, you're right, it's not a huge deal. You probably won't get a lot out of quaternions on a platform like Roblox. However, if you choose to branch out, it's almost guaranteed you'll see quaternions again. So whether you're just curious like I was, or actually want to learn and apply this stuff, you're in the right place. Before we can get into understanding quaternions, we first need to understand their origin. In order to understand their origin, we need to understand what imaginary numbers are. The name imaginary number might seem daunting, but for our purposes, the concept is pretty straightforward. Imaginary numbers have a very simple purpose: to solve equations that real numbers could not. For example, take x squared plus 1 equals 0. In the realm of real numbers, we know that we can't solve this equation because any real number we take to the power of 2, whether positive or negative, will result in a positive number. And there's no positive number that we can add to 1 that will give us 0. In other words, in order for x squared plus 1 to equal 0, then x squared must equal negative 1. In the above example, if x squared were to equal negative 1, it would be an imaginary number. I can't stress this enough. There's no logical reason some number would square to negative 1. We just accept it for the sake of being able to do cool stuff with it. One last thing. So far we've been dealing with the variable x. However, the imaginary number is commonly written as I. This is the variable I'll be using from here on out. So just remember, I squared equals negative 1. Now that we've learned a bit about I, we can actually start to look at some of its properties. To start, let's see what happens when we take different powers of I. Surprisingly, or unsurprisingly, depending on how quick your mental math is, we're left with a pattern of 1, I, negative 1, negative I, repeat. This might not seem like a big deal, but it actually shares something in common with a pattern you're probably familiar with. X, Y, negative X, negative Y, repeat. Both of these patterns are for rotating 2D points 90 degrees counterclockwise on a plane. When we hold the two patterns side by side, what you might notice is that there's always an I in the same slot that there is a Y, and there's always a real number in the same slot that there's an X. With this in mind, we can use a combination of real and imaginary numbers to represent a 2D position just like X and Y. We call these complex numbers, and we place them on the complex plane. As mentioned earlier, I multiplied by itself has an interesting property of rotating 90 degrees counterclockwise. We can use this property of I to multiply our complex number, and sure enough, we find that it allows us to rotate in 90-degree increments around the origin of our plane. We can also add, subtract, and multiply complex numbers together. This should be all very familiar to you because although we're keeping aware of I's unique properties, this is mostly just plain old algebra. The last thing we need to talk about while still in the realm of 2D is the rotor. A rotor is something we can use to rotate any point by any angle, thereby allowing us to escape the clutches of 90-degree increments. To do this, we know we can trace a circle on the complex plane via an equation like r equals cosine of theta times sine of theta, I. If we multiply this by a complex number where a and b represent the real number and the coefficient of I, we get p prime equals a times cosine theta minus b times sine theta plus a times sine theta plus b times cosine theta, I. You might actually be already familiar with this equation if you know about the 2D rotation matrix. If you'd like to see more on that, I go over the derivation on the Cartesian plane in the 2D collision article on the wiki, which will be linked in the description below. There's still a lot more that you can do in 2D with complex numbers, but because this is a video about quaternions and we've satisfied the basics of what we need to know, it's time to move on. Now that we know a bit more information about rotating points in 2 dimensions, we can set the stage for quaternions and understand why they were such a big deal in their time. Prior to quaternions, most mathematicians saw the complex plane in 2D and simply figured if they wanted to add a third dimension, they just had to add another imaginary number. Just as I is to the y-axis, they figured j would be to the z-axis. The problem was that when multiplying these complex numbers, you'd be put in a position where you have to multiply 2 imaginary numbers together. That's kind of a problem, since we don't know what the product of those 2 numbers are, and therefore can't possibly give a definitive position in space. However, Come October 16th, 1843, an Irish mathematician by the name of William Rowan Hamilton came up with the brilliant idea of adding a third imaginary number. The equation is as follows and is essential to making complex numbers work in 3 dimensions, although technically, with the third imaginary number, we're now working in 4. I squared equals j squared equals k squared equals I times j times k equals -1. This might seem a little confusing, but if we expand on what this means, it'll make a bit more sense. Check your screen. In short, Hamilton said that instead of stumping ourselves by not knowing a real number that is the resulting product of I times j, just set its product to another imaginary number, and from there we can figure stuff out. Now, a very interesting and important relationship can already be seen between Hamilton's equation and some established vector math that we already know. If we view I, j, and k as axes, I equals x, j equals y, k equals z, if we were to cross them as unit vectors, we would get a very similar relationship to what Hamilton discovered. Once again, check your screen. This finally leaves us with our finished quaternion, a plus bi plus cj plus dk. Finally, we can now actually get into the math behind quaternions. For the most part, this is all going to be algebra, so that we can apply what we learned to any numbers we plug into the a, b, c, and d values. Let's start with the concept of an ordered pair. An ordered pair, for those of you who don't know, is just a different way to store the same information. We can simply separate the parts of the quaternion that are standalone real numbers from those that are coefficients by a comma. This isn't some math trick, we're just writing this down differently, plain and simple. So why are we doing this, you might ask? Earlier we saw that I, j, and k correlate to x, y, and z, which is what we use to represent 3D space in games. As such, we can now write our ordered pair quaternion with the complex number replaced by a vector made up of the coefficients of I, j, and k. Considering complex numbers aren't the norm in game development, it's pretty safe to assume that this is the form that we'll be using. Now on to operations. In some cases, such as addition and subtraction, both the vector and complex form are pretty intuitive to compute, and just require you to either add or subtract the values in the ordered pair. No doubt. Multiplication, on the other hand, is not as simple as addition or subtraction. To get us started, let's multiply 2 quaternions together in the complex number form. I highly recommend you pause your screen to confirm the math. We can now take this expanded equation and apply the relationships that Hamilton discovered, which leaves us with this. So far, what we might have done might not have seemed to bear any fruit, but we've actually found something that makes multiplication very mechanical. Let's take a look at what each new component would be. We can further simplify this when placing all the numbers together. I've tactically placed the brackets so that you might be able to see the relationships I'm about to show you. Let's take a look at each bracketed area, shall we? If we look at the first bracket, we know that's the dot product of the I, j, and k components of both quaternions. If we look at the next 2 brackets, those are just the I, j, and k components of the 2 original quaternions multiplied by the real number part of the other quaternion it's being multiplied against. Finally, if we look at the remaining brackets, we'll see that it's simply the cross product between the I, j, and k components of the first against the second quaternion. With all this in mind, we can very easily multiply 2 quaternions with our ordered pair vector form by using our discoveries from before. Okay, a few important things we can learn from multiplication, which is why I went over it first. To start off, let's see what happens when we multiply 2 quaternions, their only difference being that their vector aspects are complete opposites. This is called a quaternion conjugate, and once again, it's pretty mechanical. Some of you might be asking what a squared plus the magnitude of v squared represents and why it's important. Well, to start off, it represents the length of the quaternion squared. How do I know it's the length? Well, because I know Pythagorean theorem also applies to the 4th dimension. In the image I show how Pythagorean theorem works in the 3rd dimension by showing how adding another dimension to the 2D space, which is where I'm sure most of you are familiar with the theorem, can also work for the 3rd dimension. I obviously can't draw the 4th dimension, but be aware that that's exactly what's going on in the conjugate, minus the square root, of course. So why is the conjugate important? The answer is simple. It helps us find the quaternion's inverse. We'll see why the inverse is important once we actually start rotating, but for now, let's just focus on actually calculating it. To make sure everything's working right, let's see what happens when we multiply our quaternion by its inverse. We should end up with some kind of identity-ish quaternion. Awesome. As we can see, multiplying our quaternion by its inverse gets rid of the vector components entirely. Okay, we're all done with the operators of quaternions, So to finish off this section, we're now going to go over a few different types of quaternions. These are still encompassed by the mechanical rules we just went over, but they just have special names. A quaternion that has 0 as its real number value, a, is called a pure quaternion. When the square root of a quaternion's conjugate, its magnitude, is equal to 1, it's called a unit quaternion. Alright, we're finally done this section. Give yourself a pat on the back, we're halfway there. Okay, so we can finally get to what we've been aiming for this whole time, rotations. Before we even get to the math, let's go over why we use them in the first place. The reason we use quaternions is that they're really good at piling up rotations in the form of multiplication. This means we can avoid things like gimbal lock and/or get smooth rotational transitions between two rotations. Before you continue, I'm going to highly recommend you watch my video on the Rodriguez rotation formula, as I'll be using it immensely from here on out. The Rodriguez rotation formula lends itself as a fantastic way for us to visualize what quaternions are doing, because we can actually easily convert a quaternion to an axis angle rotation in just 2 simple steps. These 2 rotation methods share a lot in common, but if you ask me, the Rodriguez rotation formula is a lot easier to understand mathematically, so we'll be using it as a start point for our rotations and also as a tool to check that our quaternion math is correct. Alright, here's where the tough stuff happens. As I mentioned earlier, quaternions are able to pile up rotations through multiplication. As we've learned in the Rodriguez rotation formula, the goal when rotating a vector is to rotate around an axis counterclockwise and to keep the magnitude of the vector being rotated intact. Quaternions are the same. We want to be able to rotate around an axis by any angle and to maintain the magnitude of the vector in question. Using this knowledge, we can set up our quaternion so that the vector we want to rotate is a pure quaternion. We can then multiply said quaternion by another quaternion that will handle all the rotating. We'll also make sure that this other quaternion is a unit quaternion so that when we multiply the two together, we don't change the length of the pure quaternion. Finally, we can assume that because we're representing a vector as a pure quaternion, any vector we want our rotation to return should also be a pure quaternion. So the pure/vector quaternion is pretty straightforward. But what about the rotation/unit quaternion? Well, let's look all the way back to the rotor in 2D. If we apply the same concept to our ordered pair, we can see that although the real and vector aspect are both scaled, they do in fact have a magnitude of 1. Awesome, we have a 3D rotor. Now all we have to do is try it out with the vector we want to rotate, an axis, and an angle. To make sure everything's working, let's compare to the Rodriguez formula, which we know to be correct. Using the axis of the square root of 2 over 2 in the x-axis, 0 in the y-axis, and the square root over 2 in the z-axis, and then the vector 2 on the x-axis, 0 in every other axis, and the angle 45 degrees, according to the Rodriguez formula, we should get a vector that's about 1.7 in the x-axis, 1 in the y-axis, and about 0.2 in the z-axis. According to quaternions, as we have them anyway, we'll get 1.4 in the x-axis, 1 in the y-axis, and 0 in the z-axis. Well, right from the get-go we know a few things are wrong. The first and most obvious is that the two answers are not the same. The second, and less obvious, but equally as important, is that the quaternion method changed the length of the output vector. We can also see that our output for the quaternion method is not a pure quaternion. So what have we done wrong? If you can't figure out what's wrong, don't beat yourself up over it, because the thing that's giving us trouble is our friend the fourth dimension. When we apply the rotation to the quaternion, we aren't just changing the 3D aspects, we're also changing the 4D aspects, and those screw things up. Here's the good news. We already learned a bit about how when we multiply quaternion by its inverse, we quote-unquote undo what the quaternion initially did. So what we can actually do then is multiply this new quaternion by the rotor's inverse to undo the 4D change. However, because we're doing that, we're essentially applying the rotation that we want to do twice. To clarify, we aren't undoing the 3D rotation because we're multiplying the inverse of the rotor by the product of the rotor and the pure quaternion, not by the rotor itself. So in order to get rid of the 4D part but keep the 3D part, we divide the angle we want to rotate by 2. That way, the first multiplication does half the rotation and the inverse does the other half. Ta-da! We did it! We applied a 3D rotation on our quaternion and it left us with a pure quaternion and the right answer. Congrats! We now know enough about quaternions to apply a spherical linear interpolation, a SLERP. A SLERP, which differs from a lerp in that it reaches its goal by rotating around the edge of a sphere as opposed to taking the direct path, is what we've been aiming for throughout this entire video. This is great because we represent our rotation matrix with 3 directional vectors. If we use a lerp method on the rotation, we sometimes get a sudden flip when the vector passes through the origin. However, if we slurp, we always trace the edge of the sphere and therefore never get that flip. When doing a lerp, we do so by getting the difference between two vectors, multiplying it by some percentage, and then add that amount back to the vector we're lerping from. Quaternions are somewhat similar. For one, we also need the difference between quaternions. Luckily, that's pretty easy to get. We just multiply the quaternion we're slurping to by the inverse of the quaternion we're slurping from. This gives us a quaternion that both represents the quickest spherical paths between two quaternions. It's pretty neat, huh? Here's where lerping and slurping vary. When we lerped, we multiplied the difference by some scalar percentage. With quaternions, we can't do that because then we'll change the magnitude of the quaternion, which we don't want. Remember, we're tracing a sphere, and the radius is always the same in a sphere. Instead, what we want to do is just adjust the angle in our difference to scale based on that percentage. It turns out that the way we can do this is by converting our quaternion to a Rodriguez rotation, adjusting the angle difference by that scalar, and then reconverting the quaternion again. We commonly write this operation as a quaternion to the power of some scalar percentage. So how do we convert to a Rodriguez rotation? Simply take the vector aspect of the quaternion, normalize it for the axis of rotation, then take the real number value, take the arc cosine of that value, and multiply it by 2. That's it. You now have the axis angle and you can use it with a Rodriguez rotation. To convert back, we take the cosine of the angle, divide by 2, and multiply the axis by the sine of the angle divided by 2 as well. From there it's simple. We just add our scaled difference back to the starting quaternion, and ta-da! We've done it. We've successfully slurped. Okay, so we can now actually look at the code aspect of this video. It's been a while, but we're now finally here. So first I'm going to show you a lerp. So this is straight doing the linear, going across a linear line. It's going to look wrong. So as you can see, we're just taking the components, including the position and the rotation matrix, and then we're just doing, as I said, a linear interpolation between those two things. And then we're going from 0 to 1 here, just going between the C-frame of these 2 points. So it's going to go from here to here, linear interpolation. So let's see how that looks. So it's going to suddenly flip. Let's see if we can get a better view of that, because you're going to see the top here, and it's going to suddenly flip, and there it goes. And if you think about it, it's those vectors scaling, and as soon as they hit that origin point, which happens at about 0.5, they flip like that. So let's check the slurp now, and I'll show you the code in a second. I just want to actually show you the difference first, so you can see what we've actually achieved. And we get this nice, full, actual, proper rotation this time, because we're doing a spherical interpolation here. So whoopee, we've actually got it working. So some of you might actually be already a little curious of this, especially in Studio, because there's a built-in lerp method. So actually doing all this, believe it or not, which I said at the beginning, not very useful. But if we do this, so cframe lerp cf2, and then we're going to get the exact same result as we got with the slurp. It actually might do the spin backwards, but it's going to give us a similar thing. Is that a lowercase l, I'm assuming? Hoping? Yeah. Okay, so we get the backward spin, but it's just rotating, 2 sides of the same coin, right? So that's the only difference there, but we're getting the exact same thing. So let's actually go into the code so you can understand what's happening. So first thing, we're doing a quaternion class here, and that's just some object-oriented programming. So it requires 2 things. It requires a W and a V. So the W is actually what we've been calling A so far. It's just more commonly written as W. I kept it as A though because A, B, C, D is what's commonly used as the coefficients in the imaginary number. So I figured there's no point in changing it to W until the end, because why bother making things more confusing than they have to be. V, that's just the vector. We're pretty familiar with that because we used it throughout the video. And this stuff's important. So the index isn't that important because that just has to do with object-oriented programming. The stuff that's important is the multiplication, the power, and the to-string. So multiplication, what we're doing is we're taking 2 things, right? So T is the actual first quaternion that's being multiplied against some second quaternion Q. So we're just making sure that they're both quaternions. If they are, we're going to calculate our new W and our new V. We talked about how we do that in the video. And then we're going to return a new quaternion with these new values. Power, now this is what we'd use to actually do our lerping or slurping, more or less. So we're converting to an axis angle, which we do down here, right? Because this is a method up here. So we're taking the unit, that's the axis, then we're taking the angle, and we're returning both of those things. So that's what we get up here, the axis and the angle. We then scale that angle, and then we reconvert back into quaternion. To string, that's just for printing, so it's nothing special. We're just printing the W, Q.W, and then the vector values. And then when we do this, we set the W and the V. So in terms of inverse, we take the conjugate, and we know how to do this. We went over all this. The W is that divided by the conjugate, and negative V divided by the conjugate. And we create a new quaternion with it. And then finally, we have an actual slurp method. So we have the Q2, which is actually where we're going to. So this part here, Q2 times self times inverse, is getting that difference. Then we're taking to the power of t, which we already did the meta table stuff up here, so that's the actual slurp part. And then once again, we add that back to the original, which is self. This last part here, I took it directly from the wiki. This is more or less linear algebra. It's out of the scope of this video. You can definitely find this other places, but I just took it from the wiki. It's linear algebra. It is taking a quaternion from a rotation matrix. So you can either look at this and probably apply it to your own rotation matrix, whether you're in Studio or not, because rotation matrices are going to be similar, if not the same. So you can take a look at that. I'll post a link in the description. And then finally, we have a slurp value. So we give it 2 cframes. We just do a normal standard linear interpolation on the position, right? The vectors like the x, y, and z. And then we actually handle the rotation via slurp. So we get the 2 quaternions, then we slurp between them. And this last part here, oops, phone buzz. Last part here, we put the position. And this is actually a specific way. If you put it in this specific order here with V, X, Y, Z, and W, it actually, the C-frame constructor will actually realize that that is a quaternion and accept it and give you the proper C-framed quaternion. So that's all there is to it. That's our slurp. Thanks for watching. Hope you guys learned something. And of course, I will post links to this code, this place, or more specifically this module in the description as well. So thanks, and see ya.